trying to find the pH of a solution, the first thing you want to do is you have to figure out what am I finding pH of. So write your balanced equation. If you have conjugates, so that would be something that differs by an H+, such as hydrofluoric acid and fluoride are conjugates. You have HF and just F-. They're going to go on opposite sides of the equation. They won't react together, and alkalis aren't going to do anything. So the first thing you want to do is you want to figure out what type of problem do I have. Is it strong acid, strong base? If it is, those are the easy ones that we already did. If you know the concentration of your strong acid, then you know the concentration of the H+, so the pH is the negative log of that concentration. Strong base, it was the same thing, but you find the pOH from the concentration of the strong base. If you have a weak acid, it dissociates to some degree, so you have an equilibrium constant for it. So we're going to see that we'll use the ICE tables and the K-equilibrium expression for both weak acids and weak bases. But today, we're going to look at these. So, oops, not that, this. If you have a weak acid and a strong base, or if you have a strong acid and a weak base, what do? So you have to find out how much of each of those you have. So the first thing you're going to do, you identify, I have strong acid and a weak base, or I have a strong base and a weak acid. Well, strong things react all the way. So go ahead and set up your equation so you have the strong thing plus the weak opposite thing, so strong acid, weak base. And you're going to do an ICF table. That's your initial number of moles, the change in moles, and the final number of moles. They won't go to equilibrium, they'll go all the way that they can go. It's stoichiometry. So in the end, if there's extra strong acid, you'll just find out the concentration of the acid. From that you can get your pH. If there's extra strong base, you'll just find your concentration of your strong base, and from that you get the pOH and then the pH. But if you have extra weak stuff, extra weak acid, and then you have its conjugate weak base as well, or if you had leftover weak base and its conjugate weak acid, then you have what's called a buffer. And the buffers use the Henderson-Hasselbalch equation, so we'll see those later. So let's go ahead and try one, and we'll see if we have a buffer or not. So if we have extra of the strong thing, we're going to figure out the pH. If we have leftover hydrofluoric acid and its conjugate, which would be fluoride, then we know we have a buffer, and we'll leave it for now. So the first thing I said, I'm going to write the balanced equation. So I'm going to say that I have sodium hydroxide, and I have hydrofluoric acid, and they're going to react all the way, because this is strong base, it's going to react all the way. The sodium will end up with the fluoride. This is positive, this is negative. So Na with the 1+, fluoride with the 1-, they balance each other out. And I'll take the H from here, the OH from here, and I make water. That's what acids and bases do. And it's balanced. So the next thing I have to do, if I want to set up initial change final, I use moles instead of molarity for initial change final. I need to know how many moles of the sodium hydroxide I had. So I'll start with this liters. This is my conversion factor to go from liters to moles, because molarity relates liters and moles. I have 1.5 liters of sodium hydroxide. And for every 1 liter, I have 1 mole. So I have 1.5 moles. Alright, so I have 1.5 moles of the sodium hydroxide, that's a 5. And I'll do the same thing with the hydrofluoric acid. I have 2 liters. And for every 1 liter of hydrofluoric acid, I can see that I have, it's also 1 molar, very creative, 1 mole of HF. Okay, so I have 2 moles of hydrofluoric acid, and I know they're going to react as far as they can. So what's going to happen is they react in a 1-to-1 ratio. I have less of the sodium hydroxide, so I'm going to change by using up all of the sodium hydroxide. And for every one of these, I'm going to react one of these. So since 1.5 NaOHs react, 1.5 hydrofluoric acids react, I make 1.5 of the sodium fluoride, and I don't care about the water because it's neutral anyways. This was my strong base. This was my weak acid. And this is my weak conjugate base. It is the conjugate of this guy. Sodium doesn't actually do anything. It's just the fluoride. Okay, so I'm left with no strong base. a little bit of weak acid, and some of its weak conjugate base. So since I have these two conjugates, this is a buffer. I will solve for the pH another day using the Henderson-Hasselbalch equation. And then in another one, let's see, here we have hydrochloric acid. So I've got this strong acid, and it's reacted with ammonia. Ammonia was that weak base. So let's go ahead and see what we make. I'm going to start with, write my equation, hydrochloric acid plus ammonia. Ammonia is NH3. Acids give up an H. So what I'm going to make with this, I'm going to give the H to the ammonia. I'm going to make ammonium ion. So that's going to be the conjugate of the ammonia. And I'm leaving some chloride. Let's go ahead and identify what we have so we can figure out in the end if we have a buffer or not. So this is a strong acid. Take off the H plus and we make its neutral conjugate base, so it's just a spectator. So I'm going to say, I'm going to say neutral. And then here I have a weak base. Ammonia is a weak base, so its conjugate, adding an H plus, is just going to be a weak acid as well. So now I have to find out how many moles of everything I have. I'm going to do the initial change final. So if I have 1 liter of 1.1 moles for every liter, then I have 1.1 moles of hydrochloric acid. And I'll go ahead and do this one. I have 2 liters of 0.5 molar. So that means I have, for every 1 liter, I have 0.5 moles. Okay, let's make that 0.5. So I have 1 mole of ammonia. So this is a 1. I'm going to react in a 1-to-1 ratio. So that means this is going to run out first. I'm going to change by losing 1 mole of ammonia, 1 mole of hydrochloric acid, and making 1 mole of this. And this guy's neutral, so I don't really care. I'll end up with 0.1 moles of hydrochloric acid and no ammonia and 1 mole of the ammonium ion. Okay, so in the end I have extra strong stuff left over. This thing's strong, this thing's gonna, it's already a strong acid, and then there's this weak acid that barely dissociates. So this is going to be what determines the pH. The strong thing is going to tell me what the pH is. So I want to know, what is the molarity of this HCl? Well, there's 0.1 moles. And there's 1 liter of this being mixed with 2 liters of that. So that's 3 liters. So it's going to be 0.03 continuing molarity HCl. So since it's a strong thing, I know for every 1 mole of HCl, I have 1 mole of H+. So I can figure out the molarity, or not the molarity, I can figure out, the molarity of the H+. And from that, I can say pH is equal to the negative log of the concentration of H+, which is just going to be my concentration of HCl. So pH equals negative log 0.03. Or 0.03 continuing. And so my pH of this thing is going to be 1.48. I rounded to 2 sig figs. pH is a little weird. The only digits that are significant are the digits after the decimal. So these all had 2 sig figs. Oh, 1. I take it back. I only had 1. So I'm going to make this 1.5. Final answer. 1 sig fig, 1 digit after the decimal plates. And finally, we have 5 grams of sodium fluoride are added to 100 milliliters of hydrochloric acid. Let's write out the balanced equation. I have sodium fluoride. That guy, fluoride is the conjugate of hydrofluoric acid. Hydrofluoric acid is a weak acid. This is the conjugate weak base of hydrofluoric acid. And that's going to be reacted with hydrochloric acid. This is a strong acid. And when they react, the acid's going to give up its H. So that H is going to go with the fluoride. This is positive, this is negative. HF. And then this positive sodium goes with this negative chloride, NaCl. So my products are this conjugate weak acid and this neutral salt. I've got an alkali metal and the conjugate of a strong acid. So this does nothing, it's neutral. So right away I know I don't care. So then we go ahead and fill this in. I have, let's let's see, initial, change, final. Let's find out how many moles I have. I have 5 grams of NaF. And the molar mass of sodium fluoride is, I have 41.999 grams of sodium fluoride for every 1 mole. And from that, I find out that I have 0.119 moles of NaF. So that's going to go here, 0.119, and I'll find out about the hydrochloric acid. I have 100 milliliters, that's 0.1 liters of 1 molar. So I've got 1/10 of a liter, and a whole liter contains 1 mole. I have 1/10 of a mole. Okay, so I can see this is a 1-to-1 ratio. This is the smaller amount, so I'm going to use up all of it. My change will be minus that 1/10 of a liter. And I'm going to add 1/10 of a liter here. So I end up with 1/10 of a mole of hydrofluoric acid, no hydrochloric acid, and a little bit, 0.019 moles of this conjugate weak base. So I have weak base and conjugate weak acid. Since I have both the conjugate weak base and weak acid, this is a buffer. I would use the Henderson-Hasselbalch equation if I wanted to know its pH, so we'll do that another day.